a few words about Tom and Michael. Sounds like an ice cream. Who will be leaving us, graduating and going on to something else, I guess. Restful evenings, I guess. And the other thing that is maybe worth mentioning, Monday. As some of you may have noticed, there is a little test. And I realize that the undergrads, which I guess some of you must be, have a lot going on. But believe me, shoving it back really doesn't fix it. Not as much as you wish it would. But what I can do that might at least focus your weekend is to give you some more explicit pointers of what to study, I suppose. I had asked the GSIs this week, in fact they did, to each compile, 10 questions? Which gave me 50 questions to choose from, with the 50 most essential aspects of the last 3 weeks, right? The absolute essentials. Anyway, what I could do is, I may even add a few of my own to that, but put together this afternoon a structures primer, the catechism of what you ought to know for this test. And if you, and I will promise you that I will select the questions directly, at least the first part. The first part will be questions with 2 problems, not just 1 problem. So we'll have 2 pages, go back to the standard format, 2 pages of questions, which will probably be 14, 15 questions, whatever fits on 2 pages, taken exactly from this list of questions, so you can very explicitly study and make sure you know what you've got to know. And then the last 2 problems will be, oh gosh, what have we done anyway?
Chapter 16, 17, 19.
Yeah, but what was in them? Deflection. What should we have a question on? Since you're the people that are here, maybe we should, how about a bonus for being here? What would be the preferable questions? A deflection question. Yeah, deflection. Okay, one will be definitely deflection. The other one, what? Oh, there's a choice. Combined stress or what was the other thing we did? Continuity. Oh, 3-moment theorem and stuff. Okay. Ah, so there's the choice. Which would you rather? Something on combined stress or something on continuous beams? Combined stress? How many want combined stress? I mean, I'll try and make them the same length. The length is, I mean, this is kind of ridiculous. It doesn't really matter. 1, 2, 3, 4. What? Count this. I can't count this high. It's a groundswell for, which one was this? I can't even remember. Combined stress. Okay, I think that's it. The rest of you want continuity or really don't care? Just want to go back to bed? Okay. Good. In that case, combined stress. I better remember this.
I'll remember.
You tell me after class? Okay. What was combined stress, right? Combined stress. Okay. And deflection. Combined stress, deflection. And I will email you this little primer with 50 or 60 questions, but it probably only be 50 questions. I can't think of any. So hopefully, my intent is that that'll focus your studying, don't you think, a little bit. So you don't have to, people were telling me, oh, we study 72 hours nonstop. Well, maybe for breakfast, and then so I know. I mean, it's probably, you start reading that textbook, and it is hard to put down. I realize Engel is quite a suspenseful read, but this will focus you a little bit more. Okay, and today, if you can hit the light, sir, we have one more topic, and that's going to be pre and post tensioning, which actually gets an interesting application. At the end of this chapter, he discusses the pre-stressed concrete, which I'll talk about briefly, but it's probably not that interesting, and it's not a question on the test, so what the heck. But the other thing that I think is more interesting is this idea of the post-tensioning and what you can do with that. And this, you see a lot of applications like this. This is the Bosch Areal in Stuttgart. That was the Areal is actually the buildings around it, which was Bosch's first headquarters, I guess, first workshop, and now it's kind of a swanky apartment buildings, I think. But this thing here, which I've got a couple of slides later of, is stiffened by these spokes, these tensions. It's being pulled in tension here downward. It's a compression structure basically, but is being stiffened by being pulled into additional compression. Interestingly enough. Anyway, okay, we'll talk about that in the course of things, but first let's look at cable trusses. This is almost impossible to use. This is a form that you see in the textbook. What Engel, kind of a simplified concept of it, I guess. What you see much more commonly in practice now are these fish belly trusses, or these cable stayed trusses. And this is the back of it, just like this is like set on its side here. The back is a cable, and then you have these bracing points. And this is used in this application to stiffen a point-supported glass facade, where the glass is actually hung structurally without mullions. So this is down in Detroit. See, it's a Renaissance Center. This is the Renaissance. Back behind it, see? Recognize that? Have you ever been to Detroit? You should get yourself a gun and go sometime. Anyway, these stiffen. This is a very thin glass wall. There are no mullions. This is just glued together, and to stiffen it, it's hung from these points at the top. It's actually suspended. The glass hangs in tension, and to stiffen it so it's not just a blanket in the wind that might crack. These are on the inside. Back it up as trusses to stiffen it. Anyway, they're very lightweight. I guess that's a point in their favor. They're also fairly diaphanous, or they're minimal material. So that's why they're kind of attractive. I think Peter Rice started this vocabulary of using these trusses because they're seem so as if they're made of nothing. The cables are so thin, there's not much to them. But they do act to stiffen this wall. And you can see, here, turn the lights back on. We will demonstrate here. I mean, you can pretty much imagine how it works, but we will show you if we can. Okay, you hold that. All right, so got that one. Got this one. This is the concept right here, which we will now lift free of the chair. If you have that thing, and the beam would deflect under say whatever loading's on it, you can counteract that load by putting a support. It's kind of like a flying mast or something, a support in the middle, and you can tension this cable. See, I am tensioning it. Whoa, that's a bit overdone. But you can see, I mean, I can bring it dead level if I want, or you can balance it so that there's no moment in the center. Essentially, this becomes a support out in the middle, but it's a support held up by the cable, which then again ties back into the beam. Now, this would normally attach to the beam. So by doing this, okay, it's pulling back. This force in the cable is held by the beam itself. It's not like it's another thing out here. I guess you could do it that way, but that's not the way it's done. It's held by the beam. So that means the beam has some flexure in it. It also has this axial force from this cable, because this cable is pulling, is pulling on it. And where that attaches, I mean, the way we've got it now, it attaches pretty much in the center. And in this example that he's got, it attaches in the center, but it might not attach in the center. It could attach, say, at the bottom edge. If we had, whoa, this would be tricky. Let's see if we can flip it up. Hey, come up here, Ryan. Flip the beam up on edge on the strong axis. Rotate. There we go.
Great.
Okay. Now, okay, say it were like that. Now, I might, this is a little trickier, isn't it? I knew there was a reason I did it the other way. If you attached it at the bottom edge here, you'd not be at the centroid of this beam, which would mean just the cable itself would be putting a twist onto the end of it. Because it would be, okay, we'll give up on that. It would be just like what we looked at with the the eccentric load business. It would be an eccentric load. That cable would be loading it like this, and as you tension it, it would be putting a bow into it. So you could get an extra effect like that. I mean, if you're trying to bow it upward against gravity, then you could attach it to the bottom edge, not at the centroid, and that would bow it up. Then plus you've got the piece in the middle pushing it up, and then, but then you also have the axial force. So these forces, here, turn the lights back down. These forces add up with a superposition equation like this. This is just, I mean, similar to what we did. That's why this is all combined in the same chapter, I guess. You've got an axial component, the P over A, this being negative for compression. Then you've got the flexure component that might be coming from something like that, or a point load. Then you've also got an eccentricity. Now here this would be 0 because it's attached at the centroid, but if it had an eccentricity, if there were an eccentric attachment, then you'd have an additional moment for that. So you add these stresses up, and you can find then the total stress. But the interesting part of the whole system is that you can use this to balance. You can either balance out the deflections, have 0 deflection up here, or have a 0 moment up there, depending how you want to solve it, by tensioning that cable. So let's see, and there's probably an example of this with a few numbers. This is an example out of the book, that same one where you've got a beam. It's got a couple of verticals, the cable on the bottom. This one's attached at the centroidal axis, so it doesn't have any eccentric moment. But the idea is you have a moment caused by the load, and you're going to balance it by these sticks, so that in the center, we'll say at the center line, it'll have 0 moment. Now, because if there were just one stick, if there were a 1-point load and one stick against it, well, then you can imagine you could pretty much bring the whole beam to 0 moment if you weren't worried about the dead load, minus the dead load. But in this case, that's not quite going to work, because you have 2 supports, so you're doing this to it. So it's going to, you can, depending on what the cable force is here, you can do different things. I mean, you could get the moment to be 0 at this point or this point, or you could, try to get 0 deflection. You could solve it for different criteria just by how much you pull on that cable. And the question then is how much do you want to pull on the cable to get, and in this case, I think the problem works through with 0 moment. So if you're after balancing this moment, first you want to figure out what the moment is. So this is, you look at a free body diagram just of the beam itself with the cable removed, no cable on there. And that shows you, okay, PL over 4, 120 kip feet. So that's what the moment is That's what the moment is from this load. Now you want to balance that moment, that center line moment, with these forces. With it, it's got a cable force and it's also got these guys. Well, this axial force is just going to cancel out, and you've got these forces, which will be in the diagram something like that, acting on the beam. These are those little stanchions, and this is still the beam. So, what we got? You got to find first this force. This is the loading. You assume that's the loading, and set it up. There's the moment equation for a third point loading, and you set it equal to this one. This one was 120, so you want to balance it. This is at the center line. They're both at the center line. So I'm balancing this loading against that loading so that at the center the moments are balanced. This one's 120 going, this would actually be 120 negative, right? And this is 120 positive. So they'll add up to 0. And if you do that, the only unknown here is this PS, right? And you can solve that. That comes out as 15. So now you know what the force is. You still don't know what the force is in the cable, but at least you know what the force is in that little strut, which is kind of a good start, because given that, you can go ahead and figure the cable force. You can set up a free body diagram. Here's a piece of the cable, half the cable. So it's got that. This is the little stanchion we just had. There's the 15 kips that we just figured out. So that goes on there. That would have to balance this one. Those are the only two verticals, right? And these two are the horizontals. So these two have to be the same. Then once you get this one is 15, you can look at this ratio, the slope of the cable. The cable's going to be, the cable is treated just like, it's a two-force member, just like way back when we did trusses, were two-force members. There's no moment in them. So since there's no moment, that means the vectors have to add up to a resultant that's exactly in the line of this cable. You can't have, it's impossible, we talked about this before. Hold that. Yeah, this is always a little bit, okay, I'm pulling in the direction of my arm. See? All right. All right. See, my arm is like this. Now, if I tried to pull this way, the cable follows it. Okay, and I go this way. See, the cable is only going to go in the direction I pull it. Whatever direction I pull it. It's not, you can't like, I pull this way and the cable goes down there. No. Anyway, so the sum of these forces, has to be exactly in line with that cable. So if this one's 15, and that's proportional to, let's see, the short edge. This is short and long, so 15 is to, 15 is to 5. 15. Oh yeah, here we go. 15 is to 5. It's written backwards. 15 is to 5. It's 8 is to 24. So and so there's the 20. This is 3 times. This is 3 times. So there's the 24. There's the 24 there, and it's also 24 over there. So now you've got the cable solved. Now you know what this force is in the cable, this horizontal and the vertical. Now you can go back and in this diagram, see we'd left that off. Now we can put it on there. So there's the 24. This is the 15 from up here. These are both 15. There's 24. Now this is the without the cable, right? This is the beam, and this is the beam with the cable. So you sum these two together, and you've got the entire picture, the whole system. So by superposition, you just add those up. You end up with that then. So this is the free body of the beam then. The forces on that beam. Now, once you have this diagram, you could go ahead and construct a shear and moment diagram just for fun, right? You might as well. This has no effect at all, these 24, on either shear or moment, right? This is just an axial force. This one has no effect on it. See? It doesn't affect it. How's that supposed to affect it? No, it doesn't affect it. Sorry. Only this one. This, you start here, 5, goes down 5, goes across nothing, up 15, up, over, down from 20, over, up 15, over, down. So that gives you that. And then you get the areas of those, and you can plot your moment diagram. That's exactly what we expected, right? That was the whole point. We were trying to get 0 moment. You haven't forgotten the point, I hope. The point was to get 0 moment in the center, but look at this. It didn't get 0 moment over here. Well, shoot. But it's not 120 either. If I hadn't had that cable on there at all, I would have come to 120 in the center, right? Remember? It was 120. So I did, hey, the cable did a lot. I mean, I did get down to 0. You could think, hey, what if? What if you pulled the cable a little bit more? If I pulled the cable a little bit more, oh, I guess that'd be a bad idea. I was going to say I would go up there. I think I got to pull the cable a little bit. Don't pull the cable a little bit more. If I pull the cable a little bit more, this will go down. But if I pull the cable a little bit less, okay, I pulled it too much already. I let out a little slack. Then I'm going to start getting the moment back in here, and this diagram will go up, I think. The cable force would go down, right? I'm loosening the cable, so it would go down a little bit. So somewhere there'd be probably a point where I could balance this one and this one. Now that would be an interesting point. You could figure and that would be the least moment then in that beam. Although it'd have a little bit of a wave in it, but that would be an interesting thing to try. Anyway, so that's it. Now you know the forces. We still don't know the stresses. We know the axial force was 24. The moment is 40. So the last step is to put the thing together, right? Figure the stresses. Here's the moment stress, 40. Get it into inches over the section modulus for that beam. Gives, whoa, man, oops, probably too much. 31.5 KSI. Here's the axial, 24 over the area, which is not really too much stress, 4.5. And then to combine the stresses, you use this interaction formula, right? So here's the axial over the allowable, and the question here is what's the allowable? Well, I guess somewhere maybe Engel just gave us this as an allowable for both. It's probably not too realistic, but it's probably something. It's something. So you put the actual over the allowable, and that gives you the amount, the amount of the capacity being utilized for that, which would be 19%. So it's 19% already for the axial. Then this one, the flexure over, and here you see there's already a problem right there. The actual is already in excess of the allowable. So this is kind of a dopey problem, but sorry. So that one's already over 100. That's 132. It's already wiped out just from that. If you look at the top, there you've got compression and compression, right? The top edge would have compression from the wait a minute. That's not right, is it?
It's right.
You think it's right?
Yeah. Do the joint.
I don't think it's right. Are you sure it's right?
Oh, the top's in tension. But the whole thing actually is in compression.
This is in, I was supposed to take tension. This is supposed, what does it say here? Positive is compression. Positive is compression. Okay, this is positive. This is the axial force in compression. Then it's plus or minus. The top edge, positive. That one should be negative. That one should be negative because it's been. Oh man, yeah, there's things you do sometimes. I was thinking like this, but it's not like that. We crank those things up so it's actually bowing like this, right? That with those 40s in the middle, it was dead. It didn't bend, but it has two little bumps there. Put your hand in the middle. It goes like that. Okay. So actually, this is, see, that's a, I can't go backwards. It's terrible. Oh, there it is. These are negative moments. Go on. These are negative moments. If they're negative moments, that means the thing's bowing up, right? It's bowing up. If it's bowing up, it's tension on the top. Man, okay. Well, there's another. Well, okay. So that's supposed to be a negative. This one on the bottom, it should be in compression. So this one should be a positive. Oh, we'll see. Maybe it does work out then. No, it still doesn't work out. These numbers are just flipped. So it fails any case. But, yeah, those numbers are backwards. Well, okay. 1 point off for me. All right, so moving right along. The other one counts 2 points. Oh, shoot. Yeah, it says 2 parts. All right, pre-stressed concrete. Well, let's look at this for a second. See if we get this right. Here is a pre-stressed tendon, probably in the bottom. Usually they're not just straight like that. Usually they have a nice parabolic curve in a sleeve or something because they're responding to the shape of the moment. Or in the book, I think he does some of them that are like a V to a point in the middle. Yeah, maybe that might be easier to manufacture like that. At any rate, this one's just straight across at the bottom. If I pull that, if I put a tension on it, and you'd want to do this. I mean, here's a scenario. You have a mold, you know, a form, and you put this cable in there, and you stretch the bejesus out of it, okay, and then you cast the concrete. But you're still stretching it. Don't let go of it. Now you cast the concrete. You still hold it, and then eventually the concrete cures and gets hard, right? And then you let go of it. Now when you let go of it, the concrete's going to hold it, and it's going to try to contract because it's like a rubber band. It's snapping back, and that's going to pull the concrete with it. So it puts the bottom of the concrete, it would be like it's pulling it then from the bottom edge, it'll pull it tight like that. So it's going to pull the concrete beam like that. So initially, in the mold, you should expect it to be, they probably do produce them with a slight camber, so it actually bows up even. But there would definitely be that moment on it, the dead loads on it, of course, but this would tend to arch it up. Oh, okay. Well, let's see. Does this make any sense? Well, whatever. In addition to that, that's the PE part of it. That's this part, okay, that part. There's also the compression from this part, okay, and then there's a load on it, no doubt, in the opposite direction. So this is arching up. See if we got the sign right on this. We can blame Shiga if this is wrong. This is compression, right? So this is right. Hey, Shiga, good job. This is correct. This is from this moment going upward. This is also compression on the bottom. So it's compression on the bottom from the axial force. It's compression on the bottom from the arching up, the PE moment. This load up here produces this diagram. This is the moment going downward, so it's sagging like that. So that is tension on the bottom. So you add up compression, compression, and tension, and you end up with something like that. So it's in compression on the bottom, which would be kind of a nice thing for concrete, don't you think? I mean, if you were concrete, wouldn't you rather be in compression? And here it adds up compression, some tension, and more compression. So hopefully this adds up to compression up here as well. Looks like it probably would. These two would cancel out maybe. So from the tension, let's see, you look at the two together. Let's see, this is, I suppose, under pre-stress only. Okay, no load on it. This would be this would match this diagram. So this goes with this one. The load is doing this to it, so that would be under this one. And the idea is you can put enough pretension in there that it would reduce the deflection. You can get it. So as a result, with pre-stress beams, you can make them lighter because you're bowing it upward to begin with. It doesn't have to be as heavy to resist the downward moment. Does that make sense? If the beam starts out already bowed up like this, and then I put a load on it, you know, and it just kind of comes out level, then I'm kind of back to zero. So it's almost like I only have to balance this upward and the downward part of it. Well, the result is you can have a lighter section. If you didn't have that pre-stress at all, then it would tend to, then you've just got to carry it with the strength of the steel, and the steel would have to start straining before it would pick up load, so it would sag more. So the pre-stressed beams are usually lighter sections. They're a little bit thinner, less deep, and I mean, you design it to meet the deflection criteria in any case, but because they have the pre-stress, they can meet the deflection criteria with less material. So that's the advantage of those. What else would be an advantage? I don't know. Something. Normally with the pre-stress, they're factory cast. They're not cast on site. And so, yeah, the curing is much more tightly controlled. They can be steam cured, for instance. The material, because you're doing it in a kind of factory setting, you can have a much lower water cement ratio and still be able to place it, and so you get a higher strength concrete. In fact, you almost have to, oh, I think there's another slide that says this, in fact. You almost have to have higher strength concrete to take advantage of the pre-stress. You know, concrete does creep. You know what creep is? It'll shrink. Under load, it shrinks. It's not exactly shrinking, it shies away from the load, is what creep would be. You know, if I put a load on it, it goes like that. Over time, over a long time. So if you have, that follows the grade of the concrete. If you have a very low grade concrete, like 2,000 or 3,000 psi, it creeps more. If you have a higher grade concrete, it's stiffer to begin with, denser, and it creeps less. So because if you have that if you put the pre-stress on it from those, or post-tensioning, either one, and the concrete creeps, it relieves the tensioning. Suddenly your bars could go slack if the concrete shrinks enough, right? So that wouldn't be too good. So you have to have, usually with pre-stress, you need a very high strength concrete. Does it say how much? No, it doesn't. Oh yeah, it does. Higher strength concrete, 5 to 10 KSI to reduce the creep. Oh, it does say all this. Reduce the creep, cracking, makes it stiffer. The pre-stressing tendons are super strong. These are, I mean, we were looking before, mild steel is 36 KSI. Normal reinforcing bars are 60 or 70 KSI. These are 250 or 270 KSI, so they are super stiff bars. You cannot bend them at all. You've seen these probably. They're used sometimes to guide telephone poles. The 7-wire strands, they're very coarse-looking cable. They're not a nice kind of woven cable. They're just 7 wires generally that are twisted together. And if you pick one up, you know, say you cut one out of a telephone pole guy and you have it there, you'll find it's very stiff. You can't just, it's not like a cable that you can just bend around. They are very, very stiff. They're stiff, of course they're stiff, because, well, not just that, but they have, yeah, well, they are stiff. And in fact, they're also very brittle. If you can shatter them, I guess, if you bang on them with a hammer or something. Okay, well, that's enough said about that, don't you think? Now, I thought I'd give you a couple examples of applications of this from some slides. These were old slides I did years ago. Not in '72, but not too long after, actually. This is the stadium in Munich, the one that Allianz replaced. You know, the beautiful glowing. They had the Bayerische Mannschaft, where we wanted this stadium was getting too small, and they were going to tear it down, and there was such an outcry. You can imagine, what, tear down this beautiful piece of architecture? So they built that other stadium. But this was done for the Olympics, and this is a continuous cable that runs along here. Oh, you can't see too well. Come on. There we go. This is a continuous cable, and the masts are set behind it that hold it up, and to get the curvature in the net, they had to have a point up here. You can see these are flying masts, exactly what we did there, and they run off of the cables. There's a cable that runs down under that saddle and back up. Let me see if I can find one. They go back up. I think they go up and down again or something. I forget. Anyway, but you don't have to have any mass coming down inside. Then it's all free space. So these you can see are tensioned with cables. This structure was the second big cable net that Otto did. He did the one in Montreal first, which is, if you look at pictures of it, it's a much lighter weight structure. And the reason is the post-tensioning in the Montreal structure was much, much lower, and it was allowed to flex. And it was deliberately not designed for snow loads. It was just going to be a temporary. It was a summer expo. And this structure, on the other hand, was indeed designed to carry the snow loads in München. And there was also there was a big debate between Schleich. Schleich worked on this, and so did Otto. And they did, after this, they never got along because they had a big fight over how much pre-stress should be in the cables. And Schleich wanted more, and Otto wanted less. Otto was kind of a, reed in the wind kind of guy. Let it move. Buildings are not tied down like, anyway, whatever. But it does have a lot of pre-stress, and you can see it kind of in the details, the size of the cables. I guess it's pretty massive mass. Where you really see it are down on the ground. Maybe I got some pictures of the ground. Yeah, that one you kind of see. This is really dark. It was late in the day, but that's the anchor. That big concrete klotz there is close to the size of this room. It's as wide as this room, at any rate. And a person is, that may be a person there. I don't know. It's hard to tell. But it's a huge thing. And and it's also like an iceberg. I mean, underground there's a bigger piece of it. But the tensioning in those cables is enormous, that wraps around like that to hold it stiff. Okay, anyway. So what else can we look at? Oh, a couple other quick examples maybe. This is a small glass arch that a friend of mine, Matthias Kutterer, built. I kind of helped him. See, I took these pictures. Everybody else was lifting. I said, wait, I'll take your picture. Hold that. So they're all holding it. But the idea is it's got a cable under it. This is similar to those other ones we looked at earlier. And as you pull this in tension, it puts the arch in additional compression, and that stiffens it. I don't really have a good way I could show you that, but if you have it, the ideal example, the classic, is a bicycle wheel with spokes. If you took all the spokes out, what would happen? You'd fall on the ground. Well, your wheel would also be kind of wobbly. It wouldn't be stiff. You wouldn't have a hub sitting there, but it would not be as stiff. The spokes pulling on that arch actually stiffen the arch of it, in addition to, I guess, placing the hub in the center. But they do stiffen it. Maybe that isn't a very good example. Shoot. Well, think of an egg, and inside the egg there's this little chicken. He's pulling down on the. Also not a very good example. I'll have to think of a better example. At any rate, pulling that and putting this arch into compression does stiffen it. And there are that's used very commonly. This is another example where it's used. This is the Areal that Schleich did. And this is a typical Schleich. Schleich has done several of these grid shells, and they're very thin, either aluminum or steel mullions. If it were just the mullions up there, it would not be stiff enough. The thing would be, too flexible. The uneven loading would cause it to collapse and buckle. But what they've done is they've stiffened it in two ways. These what you see with the fine lines there, that's a net. It's a complete cable net that without any tensioning, hangs naturally about a foot below the other shell. So you've got a curved shell here and a mirrored cable net shell below it, about a foot away. And then at every node, at every one of these intersections, there, you can't see it on this slide, but at every one of those, there's a piece that comes down and grabs the cable, and they screw it up. And they screw the whole thing, they screw the whole cable net up so that it rises until it touches the compression net. Well, think what that does. If the ends are all fixed, you're stretching the cable. As you push that cable net up, you're stretching it. So you're putting it into tension. And when you release, you're attaching it to the grid shell. So in essence, the tension in the net translates into the compression of the additional compression on the grid shell that has to hold it. So you're stiffening the whole grid shell by putting this additional compression on it. It's really an ingenious idea. One of the more clever things. This thing adds additional, so this is like a bicycle wheel spoke, like a hub, and these reach up and they catch a particular arch and stiffen that arch. So instead of having if it weren't for that, you'd have to have a big massive beam up there, which would not look quite as attractive. So to keep this thin and light, it's braced by this. So this is almost the same thing as what we did at the beginning of class, except it's a curved example, and it all comes down to a point. These guys, these splay up. Well, no, it isn't exactly the same. It isn't the same at all. Forget it. But they're pulling down on that arch. Anyway, kind of a graceful structure. What else? Oh, and here's our own in Detroit. This was SOM's version, and these you can see the fish belly trusses. The concept here. This is a huge truss up above that's held up. There's a piece here and a piece at the other end that hold up this big truss, and then the entire facade is just hung from that. And you can see what it is in a true point support. This one actually they fudge a little bit because they've got a cable that runs down right there. But when Peter Rice, one of the early ones was the one in La Salette, those little cube buildings. And in those, there was no second cable. That you just had the glass tied at these points, and it hung like a chain. From those points, the glass was the chain link, and then there was another fastening down here, and all these plates of glass are just like chained together with those little spider pieces. Now, in this one, they do have an additional, it's almost like a safety. They have a backup cable that runs the length of it, too, that stiffens it. But there's no mullion in it that supports the glass at all. The glass, and this is why they call it structural glass, because the glass is hanging in tension structurally. If you break one of those pieces of glass, you don't just get a hole in the glass, you get the thing go, it doesn't completely fall. Actually, when Rice did his, for La Salette, they tested it. They set the thing up and they broke one panel, and the idea was it could deform massively but not collapse, and that's what it did, pretty much that. Anyway, so here are a couple other pictures of this. Right, a close-up of that cable detail and the arch. Now, we got just 3 minutes. I don't know if I can pull this off in 3 minutes. Turn the light on. But I will give you a little reading here, which you have to listen to this carefully. It's a little bit long. It'll probably take 5 minutes. Sorry. Oh man. Okay, so we're going to go 3 minutes over, but I'll read fast. This is a description of a dilemma of structural optimization, and it's rather cleverly written, I think. And the dilemma is, if you know, in any system, in any structural system, normally there's a weak link, right? You find what piece is going to fail, and that determines the whole thing. So what if you fix that and then you go on? You know, then there's some other weak link, but you could fix them all, and that's kind of what this is about. So this was by Oliver Wendell Holmes, the deacon's masterpiece. Oh gosh, I'm going hoarse already. I haven't even started. Have you heard of the wonderful one-horse shay? One-horse shay that was built in such a logical way that it ran for 100 years to the day, and then of a sudden it, but I say, I'll tell you what happened without delay, scaring the parson into fits, frightening the people out of their wits. Have you ever heard of that, I say? Probably not. 1755, Georgius Secundus was then alive. Snuffy old drone from the German hive. I don't know what they mean by that. that was the year when Lisbon town saw the earth open up and gulp her down, and Braddock's army was done so brown, left without a scalp to its crown. Whoa. It was on the terrible earthquake day that the deacon finished his one-horse shay. Now, in the building of chases, I'll tell you what, there is always something, a weakest spot. In the hub, tire, felloe, in spring or till, in panel or crossbar or floor or sill, in screw or bolt or thorough brace, lurking still, find it somewhere. You must and will, above or below, within or without, and that's the reason, beyond a doubt, that the chase breaks down but doesn't wear out. But the deacon swore, as deacons do, with an I devum and an I tell you. He was German. He would build one shay to beat the town. In county and, I can hardly read this, in county and kearney all around, it should be so built that it couldn't break down. For, said the deacon, it's mighty plain that the weakest place must stay the strain, and the way to fix it was, I maintain, it is only just to make that place as strong as the rest. Okay. So the deacon inquired the village folk where he could find the strongest oak that wouldn't split or bend or broke. That was for the spokes, the floor, and sills. He sent for lacewood to make the thills. The crossbars were ash of the straightest trees, the panels of white wood that cuts like cheese, but last like iron for things like these. The hubs of logs from the settler's ohm, last of its timber. They couldn't sell them. Never an axe had seen their chips. And the wedges flew from between their lips. Their blunt ends frizzled like celery tips. They just don't write like this anymore, do they? Step and pop, iron, bolt and screw. Spring and tire, axe and linchpin too. Steel the finest, brightest blue. Thorough brace, bison skin, thick and wide. Boot top dasher from tough old hide. Found in the pit where the tanner died. Whoa. That was the way he put her through. There, said the deacon, now she'll do. Yeah. Do I tell you, I rather guess. She was a wonder and nothing less. There she stands. She was a wonder and nothing less. Colts drew horses. Beards turned gray, deacons and deaconesses dropped away. Children and grandchildren, where are they? But there stood the stout old one-horse shay. In other words, it didn't wear out. As fresh as the Lisbon earthquake day. 1800, it came and found the deacon's masterpiece, strong and sound. 1800, increased by 10. Handsome carriage. They called it then. 1820 came, running as usual, came much the same. 30 and 40, and last arrive, and then come 50 and 55. Little of all we value here wakes on the morn of its 100th year, without both feeling and looking queer. In fact, there's nothing that keeps its youth, so far as I know, but a tree in but a tree and truth. This is a moral that runs at large. Take it, you're welcome, no extra charge. 1st of November, the earthquake day, and there are traces of age in the one-horse shay. One more page. a general flavor of mild decay, but nothing local, as one might say. There couldn't be, for the deacon's art had made it so like in every part there wasn't a chance for one to start. For the wheels were just as strong as the thills, and the floor was just as strong as the sills, and the panels were just as strong as the floor, and the whipple tree neither less nor more, and the back crossbar as strong as the fore, and the spring and the axle and the hub and all of that. And yet, as a whole, it was past a doubt. In another hour, it will be out. Reached its age. 1st of November, 55. This morning the parson takes a drive. Now, small boys, get out of the way. Here comes the wonderful one-horse shay, drawn by a rat-tailed ewe-neck bay. Humph, said the parson. Off they went. The parson was working on Sunday's text, had got to 5thly, and stopped perplexed at what the Moses was coming next. All at once the horse stood still, close by the meeting house on the hill. First a shiver and then a thrill, then something decidedly like a spill, and the parson was sitting upon a rock at 9:30 at the meeting house clock. Just the hour of the earthquake shock. What do you think the parson found when he got up and started round? The poor old one-horse shay in a heap or mound, as if it had been to the mill and ground. You see, of course, if you're not a dunce, how it went to pieces all at once. All at once and nothing first, just as bubbles do when they burst. End of the wonderful one-horse shay. Logic is logic. That's all I say. There you go. And so